Okay, so now that you've got kind of a high-level view of about, I don't know, 8 or 9 Java synchronizers, let's start diving down into each of them, and we'll go back and forth. We'll talk about Semaphores now, and we'll talk about the other ones later. I'm trying to order these things so that what you cover in your programming assignment are what we're going to cover in the class. Always remember that the programming assignments contain links to other videos that I've already recorded from previous classes that you can watch if we haven't gotten to one of the topics. So you can always kind of get an overview, but naturally we'll cover these topics in class. So we'll talk about semaphores. I'll explain what a semaphore is. I'll talk about the 2 different types of semaphores, which are counting semaphores and binary semaphores. I'll reiterate the human known use of semaphores. You've already heard it, so we'll go through that very fast. It's the beach volleyball tournament stuff. So what is a semaphore? A semaphore is conceptually an object. So this is, not thinking about Java, just think about the concept of a semaphore. It's an object that can be atomically incremented and decremented to control access to a shared resource or to a group of resources. The concept of semaphores has been around for a long time. If you're a fan of trains, then you have semaphore flags to say stop versus clear, and these are used in order to ensure that 2 trains aren't on the same track at the same time, right? So the shared resource there would be the track, and you don't want to have 2 trains on the track at the same time, especially if they're going, together, right? That would be a big mistake. You'd have a horrible mess. So you can learn more about the origins of semaphores as used in railway transportation by looking at this link. So stop and clear are the typical things. Stop means don't go on the shared track. Clear means you can go on the shared track because you've got exclusive access to it. Concurrent programs typically use semaphores to control the interactions between multiple threads. So here's a simple example. I'm not advocating drinking, by the way. Just thought this was pretty funny. And you'll understand why. If anybody here who's a Grateful Dead fan will see why this is somewhat amusing. So let's assume, for sake of argument, we've got a bunch of threads, and we've got a semaphore, and we've got some things we want to share, which in this case are bottles of Grateful Dead wine. And why this is even mildly funny is that the Grateful Dead have this song called We Can Share That. So in this case, we're going to share the Grateful Dead wine. So we can use the semaphore to control access to a limited number of resources. So let's say we have a lot of threads that would like to consume this wine. And you can watch the Grateful Dead song at this link. I'm not really a Grateful Dead fan, but it just worked out that it kind of made sense in this context. So what we're going to do is we're going to start out with a count. The semaphore will start with a count that corresponds to the number of resources we have, the number of units. So let's say we have 3 bottles of Grateful Dead wine, and so we're going to initialize our semaphore to the value 3. And some thread comes along, it wants to drink some Grateful Dead wine, and for whatever reason, you have to have a bottle. You can't just share it, but in this particular case, since there are 3 of them, and the semaphore had the value of 3, this thread gets the bottle, and the semaphore decrements by 1, because now there's only 2 of them left. This starts to sound like 99 bottles of beer on the wall or whatever, right? In this case, 3 bottles of Grateful Dead wine on the wall. Another thread comes along. It wants to acquire a bottle of Grateful Dead wine, so it gets 1. The semaphore goes down to 1. The semaphore count goes down to 1. And at that point, when another thread comes along to acquire it, the count goes to 0. So these 3 threads have got their resource, and all the other threads are going to have to wait until someone is finished drinking the bottle. And of course, you're assuming it doesn't go to empty. I mean, the bottle's not empty, because otherwise you'd have to just keep the count to 2, or if someone drank 1. But you assume that they have maybe 1 glass at a time. Yeah. Well, so in this case, the resource, what would you say the shared resource was in this example? Right. Sure. So what are we doing in our current assignment right now? Right. So the Palantiri, the set of available Palantiri are the shared resource, or is the shared resource. So let's say, for sake of argument, we've got 4 of them, but we've got 10 beings that want to gaze. So in that particular case, the count would be 4, because we have 4 of these things. If 10 beings want to gaze at any given point in time, there'll be no more than 4 who are gazing, and the other ones are going to have to wait. So just replace the wine bottles with a Palantir or the Palantirian, and you get the same idea. If you think about other computer sciencey things that are not Lord of the Rings based or Grateful Dead based, if you're thinking about, like, I don't know, network connections to a database, you might have a database, and you might say, we're not going to allow more than 10 clients to access this database at any given time for whatever reason. Maybe it's a licensing issue. Actually, that's a good one, a floating license. If you're developing software that you want to use in an enterprise, you might charge people by the number of concurrent users, but you might set a limit. And so if somebody, or you might say, if you want the bronze package, you can get 3 simultaneous users. If you want the silver package, we'll give you 10 simultaneous users. If you want the gold package, we'll give you 100 simultaneous users, or whatever. So in that case, the resource would be the number of licenses that could be in use at any given point in time. And so you might use a semaphore to keep track of that, so you could ensure that once you had given out all the licenses to the users, anybody else would have to wait for another license to become available. So those are examples of things. Good question. Obviously, if a thread is waiting for a resource and it's not available, they can either just keep waiting forever, or they can wait for a certain amount of time. So they can block indefinitely, or they can wait for a short amount of time or a long amount of time, or just check it real quickly to see if it's available and bail out if it's not. Once a thread is done, then it will arrange for the second semaphore to increment, and then that means that the resource is available for someone else to use. There are 2 types of semaphores: counting semaphores, which, as we'll see, have a value from 0 to n. And in this case, the value of the semaphore is going to determine how many things are available, how many resources are available to access it. And so you think of them as permits, right? Or like licenses, permits. You can hand out a certain number of them. If the value is negative, then that basically means that the count has dropped below 0, and the negative count are the number of threads waiting to get the resource, because you can't get it as long as it's going to be less than 0. If it's 0, that means nobody's waiting, and that means that if you try to get the resource, you'll block until it becomes positive. And if it's a positive value, it means there's no waiting threads and there's resources available. So if someone wants it, they will atomically decrement it and get the resource. So those are basically the 3 types of states: negative, 0, and positive. The key point is, as long as the semaphore's count is 0 or less, you have to wait. You can only acquire it when it's positive. Binary semaphores are just semaphores that are a bit lobotomized, right? They have 2 values, available, not available, or busy, not busy, or whatever. So it's an all or nothing thing, or acquired or not acquired. So typically what happens there is, if the value is 0, it means that it's already in use, or it's been acquired. If the value is 1, it means it's not acquired. And so if you try to get a binary semaphore and it's already acquired, you wait till it's not acquired. If you try to get a binary semaphore and it's not acquired, you can acquire it. So the values of n are just 0 and 1. In practice, people will often implement a binary semaphore using a counting semaphore, where you just restrict the values to 0 and 1, right? So it doesn't have to be a more complicated way to do things. In fact, in Java, there's only a semaphore, which is basically a counting semaphore. And if you want it to behave like a binary semaphore, you just have to restrict your usage to 0 and 1 and give it an initial count of whatever you need. Yeah? Oh, great question. So the question is, why do we need all this stuff, right? What's the mechanism? What's the reason why we need to have a semaphore as opposed to just, int permits or something like that, right? Or integer permits? Because incrementing and decrementing a plain old int, or even a plain old integer, is not an atomic operation. So number one, if multiple threads were to try to increment and decrement it at the same time, you would have race conditions, because it's not inherently synchronized. And number two, even if it was somehow inherently synchronized, the property that's important with semaphores, which is once it's 0 or less, you wait, that isn't what you get with an int. So with an int, even if it was an atomic int, so it was thread safe, if you decrement it and it drops below 0, you just have a minus number come back to you. Whereas with semaphores, if the state is 0, you will wait until the state is non-zero. So it has more powerful semantics. So number one, it's not built-in ints or built-in primitive types like int and double and long and so on. They aren't synchronized, and they don't have these semantics that we need to be able to wait when the count drops below a certain value. We'll look at a bunch of examples of these things shortly. Just to give you a quick recap, the Palantir Simulator app, which is what you're doing for the course, uses a counting semaphore where the count keeps track of how many Palantir are available. And when you watch the video, it'll show you how all that works. So we've got a bunch of Palantiri, and we've got a bunch of beings, and those beings some of them are gazing because they've got access, others are waiting. And if you run the program and you kind of make the speed run slower so you can actually see what's going on, you'll see that underneath each of the beings it says what state they're in. Are they in the waiting state? Are they in the gazing state? If they're gazing, how far along are they? What's the max number of iterations are they going to do? So it gives you a real good insight as far as what's happening. There's a ping pong application, which you can take a look at here if you're curious, that uses a pair of binary semaphores. So they use binary semaphores to go back and forth and ping and pong and ping and pong. And so that's another fun example. I've already given you the human known use, which is the beach volleyball example, so I won't go into that in detail. The bottom line is, much as we talked about with wine bottles or Palantiri or network connections or licenses, there's this concept of a count of something, and we use that to mediate access to a shared resource or a group of resources. Okay, so that's the end of part 1 of this discussion.